we do the performance evaluation, we propose three approaches, three options, more like level 1, level 2, level 3 analysis, but it's but it's not the same thing. So level 1 is really based on actual field data, but what I'd like to talk about is this level 3 analysis option 3 analysis that we talked about. We said use Mepdg software to predict fatigue cracking, rutting, and low temperature cracking and roughness for the proposed material and for a control material that is equivalent. Okay, so for example, if it's a warm mix asphalt, then that is going to be used as a 4E3 mix. So propose the properties or predictions of Mepdg for that 4E3 material, and also come up with an equivalent design, do same mix design, same job mix formulas, somewhat similar, use the similar aggregates, and come up with a control and analyze your control. And there's the new material, there is the control material, and based on those two, we come up with a performance score. Questions so far? You should have a question. Yes.
So for the high level one, where you're analyzing actual field data, you actually then put in a test section to
Yes,
analyze
exactly.
that, and you can do that without any of the other data?
Yeah. So this is the highest level because so many people, I know that Creighton polymers and all that, they actually invest the money and they pay National Center for Asphalt Technology, NCAT. They actually pay for a section there. They put their material there. They have their section. There is a control section. That's a very good data. I mean, you can't really beat that data. That's field data, real trucks moving, even though the temperature is, you know, for Auburn's Alabama temperature, but still it's a very, very good data. So that data, we said that's the highest level. It's because it's real field data. But one thing that you should be asking a question about, I said proposed material and their control material. We're comparing proposed versus control. There should be a what if question. Let's say I'm a developer of new material. What if control is really a bad, crappy control? Right? You can come up with a new material, and you can propose a corresponding control material that is really crappy. So how do you, then, so what we did is, okay, we said, all right, control material, you can still compare against control material, but we said we're going to run a whole bunch of tests on typical MDOT mixtures. So what we did is we ran typical MDOT mixtures, flow number, beam fatigue, those kind of data, and we come up with some kind of a baseline. So you compare against your control, but also at the end compare against the baseline mixture that shouldn't be too far off from a typical MDOT material. So that's how we did this analysis. Anyway, so after the performance analysis, then what we have is this asphalt there. If you look at this, the way that it goes is once you run the pavement ME, you have predictions of fatigue cracking and thermal cracking and rutting, and the performance score is calculated, analyzed based on all these three. The way that it works is like, here's an example. So let's say you run laboratory test by the pavement ME design for level 1 analysis, and let's say you got these numbers. And then you got your performance score is based on the stress of your control material minus the stress of your proposed material divided by the stress of the typical MDOT mix. Okay, so this is essentially your performance score. And these typical distress for the MDOT mixtures, we come up with some distresses for typical structures, few typical structures, and this is how we come up with that performance score. And once you get a performance score, then that performance score goes into the life cycle analysis in the phase 2. And that phase 2 life cycle analysis is really based on present value analysis. So let's say if the proposed material has a performance score of 50%, meaning it's 50% better than the control material. So you look at, let's say, 100-year life cycle duration for, let's see how many times within that 100 years you would do a reconstruction and, start calculating the costs of reconstruction 100 years, how many times that's going to happen. The proposed material, depending on how better that proposed material is, for a 100-year period, you will have maybe less number of constructions. And then because of that, you calculate a present value because of that less number of constructions. And you compare essentially net present value of the proposed material and net present value of the control material. And all this is based on pair mean analysis. And eventually, you get an engineering performance score, you get a sustainability performance score. Sustainability that's not just the cost, there's also environmental effects. Carbon, it's quite, quite lengthy to explain everything. But the bottom line is, PME is a key engine in evaluating a new material on whether to decide to use it or not in pavements. So when you look at a performance score of 9, what you're seeing here is, in this particular example, it's essentially saying, overall, considering the sustainability, life cycle cost, performance, the new material is 9% better than a typical material. So it's good, it's not worse. You can try it, maybe it's gonna work. Remember, this includes the cost and everything. So you shouldn't be asking what about the cost, because it's in there. That's life cycle cost. The initial cost during the reconstruction, everything is in there. So we developed this software called NewPave, and that has the software. They own it. So there's while developing this software, we actually looked at one of the structures, and we evaluated multiple different mixes, and we ran a whole bunch of tests, and we ran simulations on this type of a structure. There was a 4-inch thick asphalt, and we keep varying the mixture type on this 4-inch asphalt, and we've seen some interesting results. Again, this was a very limited study, not very, very extensive, and there's really no guarantee that 9% better is going to work in every single project and every single structure and every single climate. So it's just an initial pass and fail type of analysis. But this is an interesting slide, I believe. So we just grouped. We analyzed 44 mixes. We grouped them based on design easels. These are 4E1 through 4E3. And what we've seen is for rutting, there's some variability here, but typically as you go higher in traffic level, you get less and less rutting, which is kind of expected. As you go to higher traffic level for 3E mixes, you get less and less rutting. And for 5E mixes, you get less rutting from 3 to 30 mixes, but we got some, unexpected results from 0.3 to 3 mixes. We would be expecting that they would have more rutting than the others. But perhaps in this particular case, the binder effects are dominant. Remember, when you go from E's to 30, as you increase the easels, you're really having a lot more interlocking and a lot more compression between the mixes. So effect of that is shown here, but at lower interlocking levels, perhaps binder is overcoming and there's not an excessive rutting, which is good. That kind of shows also that the overall super pave system is working pretty well. It's not really allowing, PG system is really not allowing excessive rutting, the binder property overcome and then.
Did you make these designs? Did you do like a full depth design when you did this, or did you just run it with like 2 inches of 5?
Yeah, this is just one structure.
So I guess what is your thickness of HMA that you use?
4 inches.
So you use
One
4
thin.
inches of like one mix type.
And then keep changing the mix type.
Okay.
And then just to see like one at a time analysis called OTA, one at a time analysis. Just change the structure and let's see how that affects the results.
Sometimes there is a binder grade change from like the 3 to the 10s and the 30s.
Exactly. Those are not considered at all. And also here in this study, it's by means not complete, because here we did not calibrate the material models. This is only solely based on level 1 dynamic modules inputs. To beta values we did not calibrate. So if you calibrate the beta 2, beta 3, you would get a more accurate picture. This is just a, this is an example. I'm just showing, okay, this is, you can do stuff like this to see the effect of different materials on compaction level. This is the cracking, similar results, cracking decreasing with higher level of traffic, and cracking decreasing again here. Not much difference between these three, but significantly lower cracking for 5E30. So we've seen similar results here. So now for thermal cracking, we saw nothing. All the thermal cracking, we were using a single K. They were all predicting same, regardless of the mix type. And this is the type of problem even MDOT was experiencing. So
we actually see that the 4 mixes perform better than the 5 mixes for thermal.
They do? Okay.
Yeah, that's just our experience when we do fold-up designs. I don't know how that varies from what type of analysis you're doing. In our fold-up designs, I'll change it to from like a 5 mix to a 4 mix, and it will perform better.
Is it?
Not every time, but most of the time it will.
I see. Okay. 4 is a little bit. Okay. Okay. All right. So, all right. So now. I already talked about this. Material damage were not. So what you've seen the data so far, the differences are only due to the changes in the E star master curve and G star of the binders. Not material damage levels were not calibrated for the graphs that I shown with the last 3 slides. So if you do that, then you would have probably a better idea. Okay, so another example analysis that we've done. So I'm showing you some examples of PMNME analysis that they were useful. We had a study on evaluating different chrome rubber modified mixtures. So we had a control mixture with the 5828 binder. We had a soft mixture. This is the Bennett road that we were studying. So this is the chrome rubber terminal mixture, terminal blend, 5828 plus 12% chrome rubber. This is produced by Seneca Petroleum. This is developed by ourselves, a wet process mixture, and this was a devulcanized rubber modified mixture that we've looked at. So we've done a whole bunch of testing for all these 5 different mixes. So idea was which one is going to perform better for, in a sense, for a specific case. We had a certain structure that we had in mind, and which one would perform better and worse. And so we did look at a typical thick, and we looked at a thick structure and thin structure. So our thin structure was a 4-inch AC over 6-inch base, and our thick structure was a 10-inch AC over a 6-inch base. And we used level 1 inputs for all E star and G star. We measured all these for all those 5 different combinations of materials. We used the same traffic level. And these are the dynamic modulus master curves of all these mixtures. I think this is a good time to talk about the real data. What you're seeing here is real data on 5 different mixes. So this is 58 minus 34 mix. You can see it's a pretty soft mix at high temperatures and low frequencies, and also it's relatively softer than the others in general at high frequencies and low temperatures. Again, this side is high frequency, low temperature. This side is low frequency, high temperature. Control was somewhere in here, and terminal blend was pretty stiff, and devulcanized was somewhere in the middle, and this is what we've seen. So we input these in PMNME. And also, we calibrated the fatigue model for individual. We've run fatigue tests for all of these mixes in the lab, and then came up with beta factors for individual mixtures. And then we entered them into the PMNME. And this is